Okay, so when we were here last time, first of all, I'm glad to see so many of you here because last time there were, I think, three. And we had the issue of people being at taking the ATC. I hope everybody did well. And then we had Columbus Day. You guys had 2 days off this week. That's crazy. So I'm glad you're back. Glad we can see stuff. And I think that the last time we were together, we were doing geometric series and sequences. Does that sound about right? Hi, Amanda. Yay. So I have for that. I actually had this form paper just a minute ago. The last problem we did, we were working on a geometric series and we were adding a bunch of terms. It was like something like 18 terms or something crazy. And we ended up with a really big number. It was like 27 million something. I do not know where that one went. So anyway, what I'd like to do is work on an actual word problem for this stuff so that we can see the applications and what they're going to look like in your homework. So here I am, wrapping up geometric sequences. So let's hit that and then we'll go real fast and drop over to stuff we did the other day or started on. I think that what we did was we were working on, so sorry. I lost my train of thought. My allergies are driving me nuts and I lost my train of thought. Okay, so there's an example in your book and it says, oh man, where did I lose it? Okay, here it is. A professional baseball player signs a contract with a beginning salary of $3 million. $3 million. That's what they sign up for. Okay. For the first year and the annual increase of 4% per year beginning in the second year. Okay. 4% increase in the second year and every year after. Okay. So it says that is beginning in year 2, this athlete's salary will be 1.04 times what it was in the previous year. What is the athlete's salary for year 7 of the contract? So year 7. Okay. Now, if it's a small number like what we're seeing here, 7 years, yes, you can go ahead and say, okay, let me multiply it by 0.04 and add it in. That'll give me the second year and so on and so forth. But if they wanted to know, what about if he worked 10 years, 15 years further on out, then it's going to become something that we're like, oh, we don't want to do this repeatedly, right? So when I look at this, I see 0.04 as a percentage. That means that I'm multiplying. And that tells me, okay, we're going to be in this geometric sequence kind of thing. It's not the arithmetic that we looked at before. So we need to know what the heck goes on with arithmetic sequence or with geometric sequences. So if you remember, we had this formula that said, hey, if you want to know what's going on in year whatever, we're going to call it n, a sub n, then what you do is you take your first year, a sub 1, and we multiply that by r, which is whatever your rate was, into raised to the n minus 1. And so you're not going to have to memorize that formula. It'll be there for you. Uh-oh. Did you hit your elbow, JC? Uh-oh. Entertainment for the group. You okay? All right, so you're not going to have to memorize this formula. You're just going to have to be able to use it. So when I look at this, I say, okay, for the 7th year, n equals 7 here. Then what they're telling me is take your initial salary, that's my A sub 1. What was that? $3 million, right? The $3 million, so I'm gonna stick that in. And what's the rate that we're multiplying by? 0.04, right? Because it's 4%. And raise it to the n minus 1. So what we're saying is we're going to get this pay raise every year, not the first year. The first year is just $3 million. But if we want the second year, for instance, then that'll tell me what I've got going on here. So if I just had a 1 raised here, then I would have $3 million times 1 point, I'm sorry, times the 0.04, but it needs to be the 1.04, right? Oh my goodness, I am having a hard time concentrating today. Okay, let me double check that. I'm going to double check real quick. I'm so sorry. If this was a 2, then we want 1.04 raised to the 1 times the $3 million. Oops, well, it's not right. 1.04 times 3,000,000. There we go. Okay, so the second year he would have $3,120,000. So that's what I want it to look like. So that's why they told me the 1.04. The one here says, hey, you're going to include one whole entire salary of 3 million. And then it's going to be the 0.04% raise. So 1.04. So if n is 7, then 7 minus 1 is 6 here, right? All right. So now I should be able to do this. It's the 1.04 raised to the 6th power. Now, that is not lovely. It's 1.2653. We're just going to keep that whole decimal in our calculator so that we can remember it. I don't want any rounding errors, whatever going on early. So that's what 1.04 to the 6 is. And then I'm going to multiply it by $3 million. I want to get enough zeros in there this time, honest. Okay, there we go. So what we're saying is he's going to be making $3,795,957. And it looks like 6 cents. And the question becomes, does that sound reasonable? And hopefully it does. So 4% of 3 million, that's the 120. If I had that raise, 120,000, it's going to be more because it's compounding on top of itself. But if I had that 120,000 for 6 years, then it would be around 740, right? So that sounds about right to me. We've got a little bit more than that because of the extra compounding. If I got some weird number, like I only had, like earlier, I multiplied by, I think it was 30,000 instead of 3 million. If I got a really low number, I'd know that's wrong because he's supposed to be getting raises. And if I got a huge number, like 5 million, 10 million, something like that, that's probably also wrong because he's not making that much extra every year. So I can kind of think about it and use my logic on this. Is this okay with everybody? Bless you. All right, so I forgot what I assigned you for the video for Friday. Was it polynomial functions? Yeah, were y'all able to watch polynomial functions? Get notes on that and all that good stuff? Okay, cool. So if we're completely done with geometric sequences, I'm going to pop back to chapter 3. That's where, I don't know why they add that chapter 8 stuff in right there, but they did. So I'm going to pop back to chapter 3, and we're going to talk about polynomial functions and their graphs. We already looked at that one. We found how to find a zero. I just want to make sure, again, we have an example and we're all okay and we can all do it. So let's hit finding zeros and their multiplicities. Make sure everybody's okay. Okay, that should have been in your video. I'm pretty sure that was that video. Okay, so this particular problem says, find the zeros if f of x equals 1/2 times x plus 3 times, you know what, we've done several x plus 3s. Let's do an x plus 5 times 2x minus 7 squared. And what it says is find the zeros, give the multiplicity, state whether the graph crosses through the x-axis and or touches the x-axis and turns around. Okay. Yes, this is a polynomial. So it's just a check. It's just an example. Not necessarily new notes, just making sure everybody can do what we had last Friday. Okay. And I know this one is a polynomial because when I look at the exponents on my x's, my variables, this x plus 5 guy has a power of 1 here. And this 2x minus 7 guy has a power of 2 here. So this total is an x cubed. And so it's going to look similar to an x cubed, or the little S curve thing, right? All right, so to find my zeros, what I do is I set the whole thing equal to 0. So I get rid of the f of x and I make that be a 0. So I've got 0 equals 1/2 times x plus 5 times 2x minus 7 squared. And then we say, okay, if you've got factors in there, you can take each factor separately and set them equal to 0, right? So hopefully this sounds familiar. We did this toward the beginning of the semester. So either 1/2 equals 0. Well, guess what? That's never going to happen, right? A half can't be equal to 0. So we can just automatically dump that one. It is one of the factors, but we don't have to worry about it. Or x plus 5 equals 0. That's this factor. That one could be, so we need to watch out for that one. Or that might give me a 0. 2x minus 7 squared can equal 0, right? All right. So let's go ahead and work on this one. X plus 5 equals 0. I can't have that one. I can subtract 5 from both sides of the equation. That would give me x equals -5. That's a possible 0. Okay. This one, be careful with it because remember, to get rid of a square, I need a square root to get that gone. But when I take the square root of 0, it doesn't matter. That's all good. It's just a 0. So what I've got here is 2x minus 7 equals 0. If it was some other number than 0, we would have a plus or minus there. All right, and then hopefully this one is very solvable, right? So I can say, okay, how do I get the 2x guy by itself? And I've got a subtraction, so I'm going to add 7. Both sides. 2x equals 7. And now to get the x completely by itself, I divide by 2, right? So what I get is x equals 7/2. So I have two solutions here. X equals -5, x equals 7/2. But we have to talk about multiplicity. So how many times is x equals -5 a solution? Just once, right? Because its exponent was just a 1. So this is multiplicity of 1. And how many times was this one a solution? It came from the guy with an exponent of 2. And that means that it's a double solution, right? So this one is, and I'm out of space over here, multiplicity of 2. So in our heads, hopefully we're thinking what that means for us. things that are just a solution one time, they're just going to pass right through, right? But things that are a solution 2 times, those guys are going to come down, hit the x-axis, and bounce. So when I put this in my calculator to graph it so that we can take a look at it, y equals, let's clear that stuff out. It's going to be a half 0.5 times x plus 5. Oh man, I am just off my game today. I'm sorry, guys. X plus 5, okay, parentheses. And then the other guy is parentheses 2x minus 7, close the parentheses, raised to the second power. What we think we're going to see is it passing through the x-axis at -5 and coming to the x-axis, but bouncing off at 7/2. And 7/2 is like 3.5, right? So that should be on the positive side of things. So let's see what we got here. It's kind of zoomed out, but no, that's not it. Let's be zoom 0. There we go. Now we can see it better. All right. So down here at -5, sure enough, it went through it. And up here at around 3.5, it's going to come down and bounce. So yes, it is doing what I asked. And it does look like a cubic function, right? Which we said it should look like a cubic because it had x to the 3rd overall. So hopefully that kind of ties in with all the polynomial stuff that we had from the other day. So all of this kind of makes sense and look familiar? Okay, cool. All right. So your video for this upcoming Friday is going to be all about rational functions. Rational functions are the ones where, I'm so sorry. Rational functions are the ones where things graph through it. Did I already have y'all watch dividing polynomials? Have you done long division with polynomials yet? So actually your video for Friday is going to be that one, if you haven't done dividing polynomials. So anyway, what we're going to talk about is rational functions. So here's a great example of a rational function. So this is new material. When I have these two parent functions, one is y equals 1 over x, and the other one is y equals 1 over x squared, okay? These two guys right here, when you see them, you go, hey, that's not a polynomial, and I know it's not a polynomial because the x is on the bottom, and remember that I can only have whole number exponents. So I can have x to the 0, 1, 2, 3, but this is really, if you think about your exponent rules, x to the -1, right? That's what sent it to the denominator, was whenever I had a negative exponent, that made it go to the bottom. And this one is really x to the -2, okay? So because it's negative, that put it on bottom. So I know these are not polynomials. Okay, and they are called rational function, and it should be pretty obvious. It looks like a ratio, right? It looks like a fraction. So that's why they call them rational. But when I go to graph this guy, 1 divided by x, we can definitely see by looking at the graph. Zoom standard it, sorry. That's what happens when I mess around with Zoom. Okay, I can definitely see by looking at this, if I was graphing this guy, I'd have this piece down here and I'd be tracing it, tracing it, tracing it. And when I went to go graph the top piece, I'd have to pick up my pen and then come up here and then trace like this, okay? So remember also for polynomials, all their graphs are smooth and continuous, but these aren't. These graphs are in pieces. Okay, so whereas for the polynomials, they're like cubics, nice and pretty and curvy and stuff like this. These things, I have pieces. So one there and one there. If I look at 1 over x, this guy is an odd function, right? Because the exponent is a -1 and 1 is odd. And look at this symmetry. It's symmetric around the origin. So these guys still hold all the rules and stuff that we had before. Nothing is different there. But the problem is it's not a polynomial. So we'll still be able to shift these and do stuff with them and whatever, but these are not polynomials. So they're not going to graph the same way. So when I start looking at these, I say, okay, let me look at the other one real quickly because I want to look see what it looks like. Y equals 1 over, I'm going to put parentheses because I want to make sure that the x on the bottom is what's being squared. And some calculators aren't very good at that. When that happens, look at this one. It's this piece on the left and it goes up like that. And then it comes down like this, boom, and there's another piece. So again, it's not a polynomial because it doesn't have this nice, pretty smooth graph. But this is y equals 1 over x squared, or x to the -2. That's an even function, right? And what we know about even functions is they're symmetric around the y-axis. So the stuff over here reflects over there. So even though it's not a polynomial function, it still behaves similarly. We just have to worry about these things and these things, okay? And the spots where the graph splits up, those are going to be called asymptotes. Okay. Those are going to be called asymptotes. And when we start talking about asymptotes, we say, oh, what can I do here to figure out where those are? So there's 2 different basic kinds of asymptotes, and then there's a weird one that we'll get into. And to do the third one, you have to be able to divide polynomials. That's why I asked about that video, but I don't think I've assigned the dividing polynomials yet. Okay, so we'll do that. I'll assign that one for Friday, and then we'll do the third type of asymptotes later. So what's an asymptote? An asymptote is where asymptotes, okay, asymptote. Okay, this is where the graph comes up against it's normally line. I'm going to call it a line. For our purposes, all of ours are going to be lines. But whenever you get into a higher math class, you could have like parabolic asymptotes and stuff like that. Okay, the graph comes up against a line, but it doesn't cross. Okay, at least in the end behavior. Remember, end behavior was what's happening as we get on the outsides of it, not necessarily right in the center, but what's happening as I get closer to positive infinity and negative infinity. So it's not going to cross these. So what we look at is we say, okay, what are we talking about? Well, on this one that we have right here, I'm just going to use him. Y equals 1 over x. I'm going to worry about my domain for this guy. Okay. And we know that when we talk about domain, we can't divide by 0, right? And this one's got an x in the denominator. So when x is 0, this guy would be undefined, right? So we're going to come over here and take the denominator, x cannot equal 0. So that means that if you were doing like interval notation, negative infinity all the way up to 0 would be fine. And then 0 to positive infinity would be fine. But that 0 guy is going to give me a bad spot. So when I look at this graph, let me come back to the one we did earlier. 1 over x. And I say, hey, where's x equals 0? It's right here on the y-axis, right? So when I look at that, I say, oh, there's a bad spot in my domain. It's x equals 0. So that is going to be a vertical asymptote. There's a vertical asymptote, meaning up and down, vertical asymptote, at any spot in the domain that gives us an error. And it cannot be removed. And I'll show you what I mean by that in a little bit. So it gives us an error and it cannot be removed. All right. So for instance, removed means can I reduce it out? And this one's not going to reduce at all, right? 1 over x, that's never going to reduce. So this x cannot equal 0. That's a spot. If I put a 0 in the denominator here, I'm going to get an error. Okay. So if it would give me an error and I cannot remove it, it's a vertical asymptote. So the one that we're doing right here is let me write it here. Vertical asymptote at x equals 0. Okay. I just can't do it. Just can't divide by that. All right, so let's look at a different one. I got a function here. Excuse me. I'm going to call it g of x. Here's my little definition of vertical asymptote. G of x equals x plus 3 over x minus 1. Okay, and all we're doing right now is looking for vertical asymptotes. So for the vertical asymptote, what I do is I deal with the domain. Okay, so domain to find vertical asymptotes. I'm going to be really lazy and call that VA all the time. Okay, so the problem is in the denominator. We don't care what's going on in the top, right? The problem is down here. X minus 1 cannot be equal to 0. Does everybody agree with that? So, and hopefully you will take the time to actually write this little equation off to the side. This one's not so bad, but in a minute, I'm going to show you a not happy one. And so we take the time, hopefully, to write it off to the side so that we get the experience to work these. So when I solve for x, I add 1 to both sides. X can't be positive 1. Okay. So what that means is this wouldn't reduce at all. X can't be a positive 1. That's a vertical asymptote. Okay. Any spot in the domain that gives me an error and I can't remove it. So you're just going to take the denominator and set it equal to 0. Okay. Most of the time. The problem comes in with examples like what I'm about to show you. Okay. Let's call this guy h of x. And he's going to be x squared minus 9 on top. And on bottom, he's going to be x squared plus 4x minus 21. Okay. So hopefully we are feeling really confident with our factoring skills, right? Because we need to find out what's in the denominator that's going to make this guy be 0. So I take that denominator and I say x squared plus 4x minus 21 cannot equal 0, right? The top, again, we really don't care what's going on for it for the most part. We'll see in a second where we're going to look at that one. Well, I got to factor this guy, right? If I can't factor it, I'm going to have to use the quadratic formula or something like that. But this one will factor, so let's go ahead and do that. It's an x and an x. And I need things, factors of 21. One's a positive, one's a negative. I know that because they multiply to give me a negative. And they add up to be a positive 4. So in my head, I'm thinking positive 7 and negative 3. If you need to take the time to do the AC method there, then multiply it out and do all that stuff, that is fine. But hopefully it factors out and it says x plus 7 can't be 0. And x minus 3 can't be equal to 0. Which will give me 2 solutions, and it should, because this is quadratic, I should get 2 solutions. X can't be negative 7, and x can't be 3. These are bad spots in my domain, right? Bad spots in the domain. Okay. But before we call them vertical asymptotes, we have to look and see. We definitely know they're going to give me an error in the denominator. If I put in a negative 7 up in here, that would be like 49 minus 28 minus 21, right? So that's going to be a 0. That's a bad thing. Okay, I can't divide by 0. So I know that these are bad spots in my domain, but I need to know, are they removable? And the reason I'm cluing in on maybe they will be removable is because I see this numerator here is a little more complicated than the other ones. The other ones were just like a 1 on top, x plus 3 on top. I could see if those would divide out or not. This one is way more complicated. And in fact, when I look at it, this is a square, x squared. 9 is a square, 3 squared, and it's a minus. So that's a difference of squares, and we know how to factor a difference of squares, right? So let's write it like this. H of x equals, on top, we've got x plus 3 and x minus 3. Okay, that's how that top factors. And on bottom, I have x plus 7, because we just factored this one, and x minus 3. Okay. And now I look at that and I say, hey, that'll reduce, right? I've got an x minus 3 on the top. I've got an x minus 3 on the bottom. These guys right here, the x minus 3 or x equals 3 up here, that one's removable. That's what we mean by removable. Okay, what that means is if I look at that guy, I can say, oh, I can pull that guy out because it divided itself out. It's still a bad spot in my domain. It's just not a vertical asymptote. Okay, it's called a hole, H-O-L-E. Okay, this guy over here, when I look, that went away. I've got an x plus 3 over an x plus 7. That won't reduce, right? I can't get rid of this guy. So the x equals -7 guy, that's a vertical asymptote. Okay. So what's a hole going to look like? A hole is going to be where we say, okay, there's going to be the graphs going along, and then all of a sudden we've got a bad spot. And then it's going along. So it'll be an open circle at that exact spot. So there's going to be an open circle here at x equals 3, or a hole. That's why they call it a hole. It's like it's just a spot I kind of skip in my graph, okay? And in fact, on your calculator, you're not even going to be able to see it because it's not going to like put a big open circle or something like that. So let's see what that looks like. So here we go. On top, and I'm going to put parentheses, okay? X squared minus 9 divided by, and I'm going to use parentheses for the bottom also, just because this is kind of complicated. X squared. Some of your calculators may go ahead and like you can actually do the exponent and then go back down and stuff like that. Mine's not that complicated, that advanced, so I got to put the parentheses. Okay. X squared plus 4x minus 21 on the bottom. Okay. Before I go for the graph, what I think is going to happen, I'm going to come in here and see the table of values. What I think is going to happen is I'm going to have an error at x equals 3, and I'm going to have an error at x equals -7. Okay. So when I look at this, come down to x equals 3, sure enough, look, it says ERR. There's an error. So that's a bad spot. And when I go to x equals -7, I can arrow up to that. Sure enough, ERR. So those are definitely bad spots in my domain. We found those right. We're okay. That's good. But what I need to know is this one's going to be a vertical asymptote. This one's going to be a hole. So they're definitely going to be skips in my graph. Let me see the graph here. Okay. Here is the -7 guy. That's a vertical asymptote there. It's not actually the asymptote drawing in there. It shouldn't be showing up. My calculator is trying to connect these points way up here with these points way down here. So it's called connected mode, and some calculators will try to connect them. It actually isn't there. It's actually like, oh, that's a spot we're never going to cross. Okay. And then over here, we don't see it at x equals 3, but we know there's a hole there. And so technically the calculator just kind of skipped that point is what happened. Okay. If I was graphing this one by hand, it would look like this. Okay. I've got -7. There's my vertical asymptote at -7. Okay, and then the graph comes up and it looks like this. I don't know exactly where it crosses. We'll try to find those things later. But at 1, 2, 3, there's a hole. Okay, that's one piece. That's this piece on the right-hand side. But remember, on the left-hand side, there's another piece, and that's what makes this guy rational, right? It's pieces. So it's right there. Okay, so it's on the left-hand side of this asymptote. So the vertical asymptotes are actually what tell me how many pieces I have. I have one vertical asymptote, so I'm going to have a piece on the left, a piece on the right. If there had been two vertical asymptotes, like one over here at 3, then there would be a piece on the left, a piece on the right, and there would be a piece in between the two asymptotes. Okay, so if there are 2 vertical asymptotes, you end up with 3 pieces. If there's only one vertical asymptote, which most of the time you only get one, if you have one of these, then it would be 2 pieces. Okay, so that's what we're looking at there. Are we okay? All right, so see, I'm getting close to my time limit here. Let me grab one more real quickly. We'll just worry about these vertical asymptotes, and then we'll go from there. So how about, I like this one. F of x equals x squared minus 25 on the top. And on the bottom, I've got x minus 5. There's definitely a bad spot in that domain, right? On the denominator, x minus 5 cannot equal 0, right? Which means x can't be what? X can't be 5. Yes, ma'am. Thank you. Beautiful. Okay, so if I just look at this, I say this is definitely a bad spot in the domain. It's going to give me an error. Can't use it. Okay, but I'm very suspicious because the top looks like it'll factor, right? So the top will factor. That's x squared minus 25. It's a difference of 2 squares. X and x. Oh, let me scoot up. X and x. And 25 is 5 and 5. And we know that should be a plus and a minus, right? And look at that. Sure enough, it will remove, right? So this guy is removable. And it's going to be a hole. Okay. But it's not a vertical asymptote. Okay, so once that guy is removed, I'm going to have something that looks like a line, right? X plus 5, it's just a line. So if I was to graph this one, I would see, hey, this guy kind of just looks like a line. Is there a vertical asymptote? And the answer is no, no vertical asymptotes. Okay, so the next time we talk, we're going to do horizontal asymptotes and something called slant. That's your bell, I think. All right. Thank you, ladies. Have a great day. I'll send you the link for Friday.